In the vast tapestry of the cosmos, a singular inquiry resonates with both scientific rigor and existential contemplation. Where is everybody? This enduring question, attributed to Enrico Fermi during a 1950 luncheon at Los Alamos, encapsulates a paradox that has intrigued experts for decades. The Fermi Paradox, as it is now known, juxtaposes the high statistical probability of extraterrestrial civilizations with the stark absence of any discernible evidence or contact. When one considers that our Milky Way galaxy alone harbors between 100 and 400 billion stars, many encircled by planets, and that the observable universe contains nearly 2 trillion galaxies, the expectation naturally arises that intelligent life should be abundant. Yet, despite the deployment of increasingly sophisticated telescopes and radio detection systems, the night sky remains mystifyingly silent. This silence is not a mere observational gap. It underpins a multidisciplinary challenge that bridges astronomy, biology, anthropology, and philosophy. Expert-level investigations into the paradox compel us to question the very origins of life, the frequency at which complex biospheres evolve, and the technological thresholds required for interstellar communication. The narrative of the Fermi Paradox is interwoven with the gradual but significant advances in astrophysics and exoplanetary science. Evidence amassed over recent decades, such as the refined estimates from Kepler's data and the nuanced understanding of habitable zones, deepens our insights while simultaneously amplifying the paradox. Moreover, the paradox is far from theoretical musings. It bears direct implications on humanity's future trajectory, suggesting that our technological civilization may either possess a unique legacy or confront inevitable, self-destructive challenges. In a universe where billions of stars preside over billions of potential habitats, even an infinitesimal probability of life per star could yield countless advanced civilizations. Yet, our own pioneering broadcasts and space ventures have not elicited any overt confirmations of intelligent life. This dissonance between expectation and observation compels us to confront profound questions about biological evolution, the practicality of interstellar travel, and the very nature of technological progress. Scholars and researchers have hence invested significant effort into constructing models, assessing probability functions, and exploring interdisciplinary hypotheses to reconcile this cosmic silence with the laws of physics and probability theory. Thus, as we embark on an expert-level exploration of the Fermi Paradox, we shall delve into its historical roots, examine the mathematical underpinnings offered by the Drake equation, and scrutinize an array of technical solutions proposed by the scientific community. This narrative aims to elevate our understanding of a problem whose answer may very well determine the fate of future civilizations across the cosmos. The story of the Fermi Paradox begins in the corridors of nuclear research laboratories. In a casual yet intellectually charged discussion at Los Alamos in the summer of 1950, physicist Enrico Fermi posed a question that would incite decades of rigorous inquiry. Where is everybody? Within minutes, Fermi performed rapid mental calculations based on the efficiency of interstellar travel and the geological timescales of the Milky Way's 13.6 billion-year history. His estimates suggested that even minimal interstellar exploration by a technologically advanced civilization could have led to its presence across the galaxy multiple times over. Following Fermi's initial observation, astronomer Michael Hart, in his seminal 1975 paper, formalized the paradox by arguing that if extraterrestrial societies possessed the capability for interstellar travel, they would have left detectable imprints on our planet by now. Hart's analysis dismissed a range of potential constraints, be they technological, ethical, or strategic, as insufficient to fully account for the absence of contact. Soon thereafter, physicist Frank Tipler extended the discourse by introducing the concept of self-replicating von Neumann probes. Tipler maintained that such probes, once launched, could exponentially colonize the galaxy within a few million years, a time span minuscule compared to cosmic scales. The conspicuous absence of these probes in our solar system further compounded the mystery. As the decades progressed, the discussion evolved, incorporating insights from renowned figures such as Carl Sagan and William Newman. They argued that colonization might not be driven purely by expansionist motives, and that diverse economic and cultural factors could lead civilizations to adopt more circumspect strategies. This interdisciplinary evolution of thought, spanning astrophysics, evolutionary biology, and even social anthropology, has cemented the Fermi Paradox as a central question in the scientific examination of extraterrestrial life. Today, the paradox serves as a touchstone for understanding not only the distribution of intelligent life, but also the potential vulnerabilities of advanced civilizations. One of the most significant analytical frameworks designed to approach the Fermi paradox is the Drake equation. Formulated in 1961 by Frank Drake, the equation quantifies the number of active, communicative extraterrestrial civilizations in the Milky Way via a product of several parameters. These include the average rate of star formation, R, the fraction of stars with planets, FP, the number of potentially habitable planets per star, NE, and the subsequent factors relating to the emergence of life, FL, intelligence, F, detectable technology, FC, as well as the longevity of such civilizations, L. Each parameter is steeped in rigorous astrophysical, biological, and engineering research. Recent advancements have drastically refined some of these parameters. For instance, data from the Kepler mission suggests that nearly all stars possess planetary systems, driving FP close to unity. Similarly, statistical studies indicate that roughly 20 to 25% of Sun-like stars present Earth-sized planets in habitable zones, thus informing E with greater precision. However, the remaining factors, especially those concerning the evolution of life, intelligence, and technological emissions, remain subject to considerable uncertainty. Researchers apply Bayesian methods and Monte Carlo simulations to narrow the possible range of N, the number of civilizations, revealing a spectrum from near zero to several orders of magnitude. The underlying mathematics of the Drake equation provides a number-driven foundation that underlines the apparent contradiction of the Fermi paradox. With billions of stars and an increasing number of detected exoplanets, even conservative estimates imply that the parameters collectively yield a non-negligible probability for the existence of numerous technologically advanced societies. Yet, this mathematical optimism remains at odds with our empirical silence. Such a paradox not only challenges statistical reasoning, but also forces experts to confront potential biases in our experimental designs and observation strategies. A comprehensive analysis of the Fermi paradox reveals a diverse spectrum of proposed explanations that scholars have developed to reconcile mathematical expectations with observational evidence. One broad category of solutions suggests that advanced civilizations are exceedingly rare. These rarity solutions are exemplified by the rare Earth hypothesis, which posits that complex life requires an extraordinarily unlikely confluence of astrophysical and geophysical conditions. Proponents argue that while microbial life may be relatively common, the evolution of multicellular organisms and high intelligence might involve a series of statistically improbable events, positioning humanity as one of the few, or even the first, technological civilizations. Another prevailing category posits the concept of a great filter. This hypothesis asserts that there exists one or more critical bottlenecks in the evolutionary pathway, from abiogenesis, the emergence of eukaryotic cells, and the advent of multicellularity, to the development of advanced tool use and intelligence. The great filter could either lie in our past, implying that we have already surmounted the most challenging obstacles, or it may yet lie ahead in the form of existential threats like nuclear war, climate catastrophe, resource mismanagement, or artificial intelligence run amok. Detailed simulations and statistical assessments have been employed to evaluate these possibilities, with estimates often varying by several orders of magnitude in probability. Observational constraints also form a vital segment of the discussion. It is plausible that our current detection methodologies, predominantly reliant on electromagnetic spectrum analysis, are insufficiently sensitive or improperly targeted relative to the modes of communication employed by extraterrestrial civilizations. Some theories posit that advanced societies might opt for communication pathways that our instruments do not yet encompass, such as neutrino or gravitational wave channels. Additionally, alternative hypotheses suggest that emerging societies might adopt post-biological forms, migrating to computational substrates where detectable emissions are minimized. Further explanations invoke intentional isolation or non-interference strategies. The zoo hypothesis, for example, argues that advanced civilizations may deliberately avoid contact with developing societies such as our own. This behavioral strategy mirrors ethical constructs akin to a prime directive of non-interference, aimed at preserving the natural evolutionary trajectory of less advanced civilizations. Finally, sociological and conceptual challenges are raised concerning our own anthropocentric biases and limited cognitive frameworks. Our predisposition to interpret extraterrestrial behavior through a purely human lens may severely constrain our ability to recognize and understand non-standard signatures of intelligent life. The rigorous analysis of the most prominent solutions reveals a layered and multifaceted discourse on the Fermi Paradox. At the forefront, the Great Filter hypothesis commands significant attention. By dissecting the evolutionary sequence in technical detail, researchers focus on pinpointing the critical junctures that may hinder the progression from simple chemistry to interstellar-capable civilizations. Detailed models of abiogenesis, which remains unreplicated in controlled settings despite extensive laboratory work, underscore the possibility that this initial step might represent an insurmountable barrier. Similarly, the emergence of eukaryotic cells, a single profound event in Earth's history, suggests that the transition to complex life is far from inevitable. Conversely, if the Great Filter resides in the future, several grave scenarios emerge. Extensive statistical and computational studies have simulated the impacts of self-destruction via nuclear arms, runaway climate change accelerated by anthropogenic forces, or catastrophic outcomes from unchecked artificial intelligence. Each of these potential future filters is supported by a synthesis of historical data, evolutionary biology, and modern technological risk assessments. Such analyses have direct implications beyond academic interest, potentially serving as cautionary frameworks to guide policy and research in humanity's own technological pursuits. The rare Earth hypothesis, while sharing overlap with the Great Filter concept, provides another explanatory dimension. Detailed analyses of the galactic habitable zone, the stabilizing effects of a significant lunar body on planetary axial tilt, and the role of large gas giants in mitigating cometary bombardments all contribute to an intricate portrait of Earth's unique biogeophysical environment. Advanced simulation models that incorporate stellar evolution, planetary geodynamics, and atmospheric chemistry further elucidate the rare convergence of conditions that have allowed complex life to flourish here. The zoo hypothesis adds an extra layer of complexity to the narrative. It posits a deliberate strategic choice by advanced civilizations to maintain isolation, either to avoid interference or as part of an ethical framework that protects nascent cultures. Evaluations of this hypothesis require not only technical insight, but also a deep understanding of sociocultural evolution and game theory dynamics. Even the simulation hypothesis, advanced by Nick Bostrom, introduces a radical perspective that the observable universe may be an artifact of computational design. Hence, the absence of other intelligences is a programmed limitation rather than an empirical deficit. Each of these key solutions is buttressed by rigorous technical analyses, advanced computational modeling, and a synthesis of interdisciplinary data, forming a robust yet unresolved debate that lies at the heart of the Fermi Paradox. Recent decades have witnessed transformative developments that have significantly refined our understanding of the Fermi Paradox. The deployment of instruments such as the Kepler Space Telescope has yielded precise measurements of exoplanet frequencies, revealing that Earth-sized planets are not only common, but may also populate the habitable zones of red dwarf stars, a finding that expands the statistical basis for potential life. Detailed spectroscopic analyses have begun probing the atmospheric composition of exoplanets, and preliminary data hint at biosignatures that could one day be confirmed as indicators of extant or extinct life. Concurrently, high-profile initiatives such as Breakthrough Listen have revolutionized the technological landscape of SETI research. With investments exceeding $100 million, modern SETI projects utilize an array of radio telescopes and advanced signal processing algorithms to scan not only for conventional electromagnetic pulses, but also for a broader range of technosignatures. These include transient laser emissions, and unusual atmospheric pollutants that could be the byproducts of large-scale industrial activity. Astrobiologists have further expanded the conceptual horizon by studying extremophiles in extreme terrestrial environments, which in turn informs models of possible extraterrestrial biochemistries. Researchers now consider subsurface oceans on moons like Europa and Enceladus as prime targets for future exploration, given that these habitats might offer more stable conditions than volatile planetary surfaces. Additionally, the dark forest theory, popularized in recent science fiction and supplemented by formal game theoretical models, offers a strategic perspective suggesting that silence may be a collective security measure adopted by civilizations wary of revealing their location in a potentially hostile universe. Collectively, these emerging perspectives and technical advances underscore the dynamic nature of the field. They stress that our current methodologies, while robust, remain in a state of evolution, continually refined by improvements in observational instruments, computational modeling, and interdisciplinary collaboration. The intricate tapestry of the Fermi Paradox carries profound implications for humanity's trajectory. Crucially, the mystery of the missing extraterrestrial civilizations serves as a dual-edged lens, one that reveals the possibility of being uniquely endowed with advanced technology and simultaneously a stark warning signal regarding the potential self-destructive tendencies inherent in technological progress. Advanced models indicate that if civilizations routinely navigate treacherous transitions to interstellar capability, the frequent occurrence of catastrophic failures may suggest that our own future is fraught with comparable existential risks. On a technical front, this analysis informs debates around messaging extraterrestrial intelligence, MEDI. The strategic calculus involves weighing the benefits of open communication against the potential vulnerabilities exposed by signaling our presence to unknown entities. In a rigorous risk assessment framework, even the smallest probability of hostile contact necessitates caution, further emphasizing the need for robust international protocols and interdisciplinary consensus. Beyond immediate technological risks, there is an enduring philosophical and scientific imperative. Understanding the Fermi Paradox may recalibrate our perspectives on sustainability, resource allocation, and long-term cosmic stewardship. Should humanity find itself as one of the few, or perhaps the first, we bear an extraordinary responsibility, a duty to preserve and expand the legacy of intelligent life in an otherwise silent cosmos. These insights, derived from meticulous mathematical modeling and historical precedent, underscore the critical need for proactive, informed measures to secure our future against both internal and external threats. In summary, the Fermi Paradox embodies one of the most profound puzzles at the intersection of astrophysics and philosophy. The enduring silence of the cosmos, juxtaposed with compelling statistical arguments and cutting-edge observational evidence, challenges us to deeply reconsider our understanding of life, technology, and cosmic destiny. Through historical analysis, rigorous mathematical modeling with the Drake equation, and the categorization of myriad potential solutions, we are compelled to confront both our unique potential and impending vulnerabilities. As our scientific instruments and theoretical frameworks evolve, so too does the hope that one day, the silence of the universe might give way to revelations that fundamentally alter our self-perception and trajectory. This contemplation, deeply technical and profoundly existential, remains at the very heart of our quest to understand not only cosmic emptiness, but also our own role in the vast, challenging expanse of the universe.